to measure integration and linear analysis class. In our previous video, we checked the basic definitions and theorems that we need in order to understand Riemann integration. So if you have not yet watched the first video, I will urge you to watch the first video so that you can have a better understanding, as we'll be checking the exercises under section 1a in this video. So in this video, we'll be checking the first 5 exercises in the book we are using, Sheldon Axler. So we'll be checking the first 5 exercises. My name is Sunday Luafemi, going to be a PhD student from the Department of Mathematical Sciences, Indiana University, Indianapolis. So the first question. The first question in the textbook we are using, we have suppose f, a function f, and domain a, b to r is a bounded function such that the lower Riemann sum, you can check the previous video to understand all these notations, and then the upper equals to the upper Riemann sum. And don't forget to like and subscribe to this YouTube channel. So we have for some partition P of A, comma B. So we have to prove that f is a constant function on the entire interval A, comma B. Alright, so let's check the proof and see how it goes. Proof. So once you check that prove that this function f is a constant function. So first, we are given our lower Riemann sum to be equals to the upper Riemann sum. So let's first of all define that. So in our previous video, we have our lower Riemann sum to be defined as the summation of the subintervals j equals to 1 to n infimum f over the interval sj minus 1 sj. So that means that we have a partition. So let me put that here. Let P be any partition A, comma B. So that means that we have our P to be equals to A naught less than x1 dot xn, which is the last one, and that will be equals to B. We have this as A, then that equals to B. So we have that as our partition. Then the definitions of this lower Riemann sum follows. So similarly, we also have the definitions in our previous videos. We checked the definitions of upper Riemann sum to be summation of j equals to 1 to n sj minus sj minus 1, the sup of f sj minus 1 sg. So by our hypothesis, we have the lower Riemann sum to be equals to this. So then we can say that by hypothesis, by the given hypothesis, so we have summation j equals to 1n sj minus sj minus 1, the sub f sj minus 1 sj is equal to the summation j equals to 1n sj minus sj minus 1, and then the infimum f over sj minus 1 sj. So, and then this implies, so we can actually have this to go, since we have the same thing here. So for all j's, so we have that also for all j's, that is j equals to 1 dot n. So we have our sub f sj minus 1 sj equals to infimum f sj minus 1 sj. So by the properties of supremum and infimum, so by properties of supremum and infimum, so we have our f to be a constant function. So let me show the graph of what that means. So we have this, we have a, b, then we have a constant function c. So that means that our function have to be a constant, is straight line on the entire interval a comma b. So that means that no matter how we divide our partition, our infimum f over the entire interval ab will still be the same, because they are of the same equal height. So that means that our function f has to be a constant function. Or else our, by the definitions of supremum, f over the same interval, it will be greater than the our infimum f. So that is that. So let's go to the second question. So as problem 2 from the textbook we are using, we have suppose a is less than or equals to x, less than t, less than or equals to b. Then we define a function f, it will be to r by f of x equals to 1 if x is less than x, less than t, and we have a 0 otherwise. So here is the question. As just prove that f is Riemann integrable, and then a comma b, and that the integral of a to b function f equals to t minus x. So we know in our previous video that a function f is Riemann integrable if the upper Riemann integral is equals to the lower Riemann integral is equals to the function. So in other words, we want to show that the upper Riemann integral is equals to the lower Riemann integral, and this is equals to integral ab of f, and this is equals to t minus x. So let's take it one after the other. So the first thing is to let's get the graph of this so that it can be easier for us to understand. So this function is of this form. So we have we have our A here, and then we have our B. In between we have X. Let's say X is somewhere here, and then T can be somewhere here. We have our 0, then we have 1. So this is just like a step function. So from X and T, from this point, our function is 1. Then otherwise our function is 0. So at this point we have our function to be 0 by the definition of the function. So now we need to define our partition, and we need to be very careful with the way we define our partition so that we're able to capture the entire point of continuity and then discontinuity. So let's define our function in this form. Let's say our A to be x0, and then define another interval here, and let that be x minus 1 over n. Then another interval here, that should be s plus 1 over n. Then another point here, then that should be t minus 1 over n. Then another point here, that should be t plus 1 over n. And then have this b to be our xn, to be our last point. Okay, whatever. So with that now, so let's partition P be, we have a comma x minus 1 over n, s plus 1 over n, t minus 1 over n, t plus 1 over n, and then our b. Okay, so we are going to check what happened on these sub intervals we have. Okay, so let's check. Let me put the interval here explicitly so that you can understand. So we have a first sub interval, we have a comma x minus 1 over n. Then the second interval we have s minus 1 over n comma s plus n. Then the third sub interval we have t minus 1 over n. Okay, we have s plus 1 over n, sorry, and then t minus 1 over n. Then the next interval we have t minus 1 over n, t plus 1 over n, and lastly we have t plus 1 over n, and then b. So let's check, and then don't forget the definition of our upper Riemann sum and then lower Riemann sum. So let's see. By definition, we have our upper Riemann sum to be equal to the summation over all the interval sj minus sj minus 1 sub f over that interval so here now j over n depending, so you have to be very careful with that also. So we have this for the logarithmal sum. Also just change the sub to infimum f sj common sj minus 1, so there is sj minus 1 sj. Okay, so if you check on this interval, let me drag this a little bit downward. So, and then let me pull down this graph a little bit down. Oh no, it's not what I want. Okay, so let's put it down a little bit. Okay. So let's see what happened on this interval. So let me put sub upper argument sum here. And then I'll put the lower argument sum here. And don't forget the definitions. So on this part, on this first sub interval, you will see that the length here, okay, let me use another ink for this one. Lower fp a common b. So on this first interval, our length will be x minus 1 over n minus a. Then if we check here, at this point, these 2 points, you will see that our function here is entirely 0. So that shows that the supremum of our function here will be 0. And then for the second interval, but okay, let's check this also. So for the lower Riemann sum, the infimum also will be 0 because our function is entirely 0 at a common x minus 1 over n at this point, these 2 points. So our function is entirely 0. So for the next sub interval, the length will be s plus 1 over n minus x plus 1 over n. So let's check. So here you see that our function is 0 and then also 1. Our function from these 2 points, this point and this point, so we have 0, we have 1. So the supremum of this function, which is the greatest lower bound, the least lower bound rather, the least lower bound, which is the supremum, will be 1. However, the infimum of this function at this point will still be 0 because that is the greatest lower bound. So the greatest lower bound between 0 and 1 is 0. but the least upper bound between 0 and 1 is 1. So let's check the next subinterval. For the next subinterval, we have the length to be t minus 1 over n minus x minus 1 over n, t minus 1 over n minus x minus 1 over n. So here now we are dealing with this entire point. So at this entire point, our function is 1. So the supremum will be 1, and then the infimum of our function on that subinterval also will be 1. Alright, third subintervals, we have length to be t plus 1 over n, and then minus t plus 1 over n. Likewise, we have t plus 1 over n minus t plus 1 over n. Okay, so at this point also, see that our function is between 1 and also is 0. So that means that the supremum function, which is the least upper bound, here will be 1, whereas the greatest lower bound will be 0. So I hope that is clear, and if there's question, you can drop your question in the comment box. I'm going to attend to it. Okay, lastly, in last interval, we have b minus t minus 1 over n. We have b minus t minus 1 over n. So here is outside the our function, where the function is 1, so everything is 0, the supremum is 0, and the infimum also is 0. Now we can now calculate our upper Riemann sum and the lower Riemann sum. So here this gone, because of that 0, this gone, this gone, this gone, this gone. So we have 3 contributions for the upper Riemann sum, whereas we only have this guy that contributes to the lower Riemann sum. So our upper Riemann sum will now be additions of all those guys. We have x plus 1 over n minus x plus 1 over n plus t minus 1 over n minus x minus 1 over n plus t plus 1 over n minus t plus 1 over n. So I'm just writing all these guys. So we have that. So what do we have? We have this gone. Which is again, we have this gone, and then what again? This is gone, this gone. Then what do you have left? So we have t minus x. We have minus n. Oh, we have plus n. This gone. This also is gone. Then we have plus n, and that should be 2 over n. So let's check the calculation for the lower Riemann sum also. We only have 1 contribution for that, and that is t minus 1 over n minus x minus 1 over n. So this also equals to t minus x minus 2 over n. So now, don't forget the definitions of Riemann integral, and that is let me state the definition. We have the upper Riemann integral, which is equals to the infimum over the partition of the upper Riemann sum, and then the lower Riemann integral is the supremum over the partition of the lower Riemann sum. So that means that these both guys, as n tends to infinity, taking out the supremum, so this guy is going to tend to t minus x, and this guy also is going to tend to t minus x. So that implies that the upper Riemann sum is equals to t minus x, the upper Riemann integral, and this also equals to the lower Riemann integral, which is also equals to t minus s for sufficient large n. So that means that the upper Riemann integral is equals to t minus x, the lower Riemann integral is equals to LF of p. So by definition of Riemann integral, f is Riemann integrable, and integral ab over that function also equals to t minus x. And that completes our proof. So don't forget to like this channel, subscribe, and then share it to fellow PhD graduate students. So next we go to question number 3. Question number 3. Okay, you have suppose f a b to r is a bounded function, and then you have to prove that f is Riemann integrable if and only if for each epsilon greater than 0 there exists a partition P of A comma B such that we have this theorem holds. So this is a nice theorem. Now once we are able to prove it, it will be the theorem we will continue to use to prove other problem. It's a nice theorem to know and to also prove. So once a function is f Riemann integrable, then we can say that the difference between the upper Riemann sum and then the lower Riemann sum is less than epsilon for any epsilon greater than 0. So let's check. Let's first of all prove the forward direction because of the word if and only if. So we have proven two things. We have to prove that if f is Riemann integrable, then this holds, and we also have to prove conversely that if this holds, then f is Riemann integrable. So let's pick the fixed direction, which is if f is Riemann integrable, we want to show that for each epsilon greater than 0 there exists a partition P of A comma B such that this holds. Okay, so by definition we have, by definition of Riemann integrable, since f, our function f is Riemann integrable, so that implies that our upper Riemann integral f of p is equals to integral ab of f. So let's denote our integrals to be I. Let I equals to integral ABF, so that it will be easier for us to handle. And also note, we have this fact: by the properties of supremum, we know that, so take note of this fact, the upper Riemann integral is less than the upper Riemann sum. Why? Because this is infimum P U of FP, comma AB. So by the properties of infimum, this is less than or equals to this. So with that fact in our mind, then we can say that we have for any epsilon greater than 0, there exists a partition P1 such that so since this is greater than this, that means that the upper Riemann sum over that partition P1 is greater than or equal to this, because this is greater than this and this is equal to this. So if we subtract a small epsilon as possible enough epsilon over 2, then this will be strictly greater than that because of this value. So similarly, we also have this fact that the lower Riemann integral is greater than the lower Riemann sum. Why? This also by properties of supremum, because this deal with sup of P over L of P. So the supremum will make this to be greater than this. Okay, sorry, this is the supremum of the lower Riemann sum. Then with that, we have that fact. So also, we can similarly say that for any epsilon greater than 0, likewise, there exists a partition. There's a partition P2 such that the lower Riemann integral, so the lower Riemann sum now P2 A comma B is less than integral B F. Okay, sorry, so we have this to be less than this. So sorry, this should be plus, so that will make it strictly greater than. So take note of this, that should be plus, so that will make it more strictly greater than, and then this will be negative, and that will make this to be strictly greater than that. So having these conditions, then we can now go ahead and prove that the upper Riemann sum, the difference between the upper Riemann sum and the lower Riemann sum, is less than epsilon. Okay. So take note of this point. We have this to be infimum. So this should be greater than, Then I will explain that. Then this should be less than. Why? Because we have this fact that the upper Riemann sum, the upper Riemann integral, which is the infimum, is less than this. So if we substitute this guy, and then by this addition, this will make this to be less than this. And then also we have these properties that the lower Riemann integral is greater than or equals to the lower Riemann sum. Why? Because this is the supremum of the lower Riemann sum. So if we subtract sufficient epsilon over 2 for the Riemann integral, then this, our lower Riemann sum, should be greater than this integral function. So please take note of that correction, and if there's any comment or any question, you can drop it in the comment section. All right, so then we can now define a refinement partition. Let P be a refinement. Let P be a common refinement of the two partitions we have defined, P1 and P2. That is P is the union of P1 and then P2. So by the properties of let me check that to be by theorem the refinement of a partition of a lower Riemann sum is lower than this. So that is by theorem 1.6 by theorem 1.5 of the textbook we are using. We have our lower Riemann sum of Fp. So since this P is refined, it is refinement of P1 and P2. That means that the lower Riemann sum of this P will be greater than the lower Riemann sum of this P2. But in other way hand, the upper Riemann sum of these will be less than the upper Riemann sum of this. That is, we have something like this. The lower Riemann sum over partition P2 is less than the lower Riemann sum over the new refinement partition, and that is also less than the upper Riemann sum, and this is also less than the upper Riemann sum over the partition A, B. So following this, from these two, combine these two inequalities and taking their difference, so we have the upper Riemann sum P1 A, B minus this. So you have to be very careful of your inequality here. So this should be strictly less than. If we translate this here, we have integral AB f plus e over 2 minus integral AB f plus epsilon 2 over this. So what we did here is just, you can translate this one, you can flip this one. Okay, then once you flip this one, you have something like integral AB f minus epsilon over 2 less than logarithmal sum fp2 a comma b. So with that, you can now perform the operation easily. You can add. By the time you add these two, then you flip, you cross this one to the other side, then you take this one to this other side, then you have this result. So then we have, oh sorry, I've made some mistake. This should be the new partition, the refined partition, this. Okay, so then we have the logarithmal sum minus logarithmal sum of the refined partition to be less than, if we open the bracket of the this is gone, and then we also have, sorry, this is minus half, pardon, so we have external, this is from here, so it's minus half, so we have plus half, and then plus half, and this is less than epsilon. So this implies that the logarithmal sum minus the logarithmal sum is less than epsilon. So that proves the effects direction. Okay, so then we can now also check the second direction. So the second direction is if for each epsilon greater than 0 there exists a partition P of a comma b such that this hold, they want to prove that the function f is Riemann integrable. Alright, so let's check. So conversely, so assume for every epsilon greater than 0 there exists a partition P such that the logarithmal sum minus the logarithmal sum is less than epsilon. So what we want to prove, so we want to show that the sup P of the logarithmal sum by definition of Riemann integral is equals to the infimum of P. So this to be the sup of the logarithmal sum, infimum of P, the logarithmal sum. So that is what we want to prove. So by definition, by definitions we have we have our logarithmal sum. We know that our logarithmal sum so from here we have our logarithmal sum. So to be plus e, or by this should be by assumption. It's equals to the logarithmal sum. That's just by the assumption, and then we know that this upper Riemann sum is less than also note note that the upper Riemann sum is greater than is greater than or equals to the upper greater than the sup. Let's use this now. The infimum P U of FP comma AB, and these are the definitions of the upper Riemann sum. So if we substitute this guy for this, then we should have the lower Riemann sum FP A comma B plus epsilon to be greater than, because this is greater than this, so we have greater than U F comma P. So if that holds, then we can have our lower Riemann sum to be greater than U of F comma P minus epsilon. So similarly, we can do the same thing for our supremum. Then similarly, we have our lower Riemann sum. So by the hypothesis that is also given, by the assumption that we have this, we can do with the upper Riemann sum. The upper Riemann sum also is less than epsilon plus the lower Riemann sum. So then we also know that the lower Riemann sum so this one is less than or equal to the sup of the lower Riemann sum. And this is the definitions for the lower Riemann integral. So if we also substitute this here, then we are going to have, we have to be very careful of your inequality. We have U F of P A comma B to be less than the lower Riemann sum plus epsilon. Okay, so if we combine these two, so let's see what we are going to have. If this holds and then we combine these two, then we have, let's flip this so that we can have our inequality. And let's flip this so that our inequality can be on the same road. So this is the same thing that we have in U F of P minus epsilon less than the lower Riemann sum. So then what do we have? If we take the additions of these guys, so we have this is less than this. So what just add up this. Then let's check carefully. Then we have the upper Riemann sum. Then if we cross this to this side, we have minus the lower Riemann sum. It's less than. Then we cross this to this side. What do we have? That's not nice enough. Let's see. Okay, here I have something not nice, but let's see. We have the lower Riemann sum minus this. Okay, then we have epsilon. Just epsilon. That is not nice enough. So let's see. That should not be true. That should not be true. Something must be wrong somewhere. So let's check. Let's try to cross check. It's wrong. We have this. This odds. With this odds, we have Riemann sum of this to be this. Okay. Then we have this. Then we have this. Then we add up these two. So we have of those two, we have this and this. Okay, so let's remove this. Then we can just write out what you have. So we have this, the lower Riemann sum to be greater than the upper Riemann integral minus epsilon, and then we also have the upper Riemann integral a comma b that's also less than the lower Riemann integral plus epsilon rather. So then we can now make conclusion by refining the partition. So you can make a conclusion by refining the partition. Partition being the bounds for the upper Riemann sum and then the lower Riemann sum. Sorry, the upper Riemann integral and the lower Riemann integral we hold for smaller epsilon. So as the epsilon tends to 0, these two, so in the limit as epsilon tends to 0, so then we have these two guys to be equal. and this proof that our function f is Riemann integrable. Okay, that is a long proof. So we'll continue the next problems in the next video.